Hey everybody, so we are looking at this problem 0 1 matrix. Given an m cross n binary matrix MAT, return the distance of the nearest zero for each cell. The distance between two cells sharing a common edge is 1. We are given this matrix over here. We are supposed to find out the nearest zero from each index. So from here, I can say the nearest zero is itself. The distance would be 0. From here, the distance would be 0. So if I create the output matrix which I have to return, and that would also be m cross n, the distance from 0 to 0 is 0. Very similarly, 0, 0, and this one 0. Over here, from 1, the distance to the nearest 0, I can go in every direction like this. And in every direction, I see the distance is 1 because the cells sharing a common edge have a distance of 1. So this is distance of 1, 1, 1, and 1. The minimum would be 1. So over here, 1. This 0. So I can say, okay, distance of 0, 0, 0, and 0. And this would be my output. If we take a look at another example, if I have this matrix, then the output would be from 0, distance of 0, from 0, distance of 0, 0, 0, and over here, distance of 1. Over here, distance of 0. Over here, I can go up, I find a 0. If I go right, I don't find a 0, but I can go forward. I can look here, I can look here, and after that I can look here, or from here I can look at here. So if I go in this way, I get a distance of 3. If I go this way, I get a distance of 3. Or if I go this, this, and this, I get a distance of 3. But if I go up, I get a distance of 1, and I need to take the minimum. So the distance would be 1 over here. If I'm looking at this element, above, I don't have 1. Sorry, I don't have 0. 0, I don't have 0. But from here, I can go here. 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 This would be a distance of 2, distance of 2, distance of 2, distance of 2 again, and distance of 2 again. So the minimum would be 2. So over here, I can say distance of 2. From 1, I can go to 0. And from all these directions, the length would be longer. So I can say, okay, distance of 1. And this would be my output. To solve this problem, what we can do is we can take a look at this element and we can go forward in right at the bottom, and if there were other indexes around it. And from every index, we can find out its closest 0. So for the case of 0, it would be the cell itself. So we don't have to go any further and we can assign it to 0. For case of something like this, we can go in every direction from 1 and we can look for 0 and we can take the minimum of that, which means we have to do it for all of these elements. But what if we have an example like this? We have 1, 1, 1, 1, 1, 1, 1, 0, and 1. In this case, if I'm starting from here, then I would basically travel until this 0 and in every way, and I would find out the minimum. Here, that would be 1, 2, and 3. I would do the similar thing for this, for this, for this, for this. If you see from over here, we are finding out 1 plus the minimum distance from this. Very similarly, we are, when we move down, we are doing 1 plus the minimum distance from here. So why are we solving the same problem again and again? Can we reuse these results? Can we reuse these results? And yes, we can. So to solve this problem, let's take a reverse approach. Instead of going index by index, how about we start from 0 and assign the minimum distance to every index where we see 1. Let's take an example of this. Let's say I have a matrix like this. I start from the first 0 I have. I move forward in every direction and I'm assigning the minimum distance from 0 to every index. Over here, since the minimum distance from 0 to 0 is 0, I would not assign it anything. And then I can continue moving until I find something that is not 0. From here, I can go over here and say, okay, I got a 1. At what distance did I get a 1? I was traveling from 0. I got a 1 at a distance of 2. Okay. So let's create another matrix. This is our result matrix. Every time I have a 0, I can say that, okay, the distance is 0. So let's assign it 0, 0, 0, zeros over here. Okay. Every time I have a 0, it's assigned a distance of 0. So from here, I move right, I move bottom. It's a total of distance of 2. So I can over here say, okay, I found 1 at a distance of 2. Then it moves even further. It goes till this one, a distance of 3. So I can say, okay, minimum distance of 3. Now, as you can see, this answer is incorrect because the minimum distance for both of these is 1. These are the closer ones, right? So let's do a thing. Let's move forward in the algorithm. Now let's consider this 0. This moves forward down. It looks at 1 and says, what is the older minimum distance? 2. So this 0 says, I can assign it a better minimum distance of 1. So how about we remove this 2 and call it 1? This is a better distance. We need to find the minimum. So we found something lesser. And then it moves even further. It comes over here and it says, okay, found another one at a distance of 3. I can give it a better distance of 2. So this 3 receives a 2. Now it travels in every other direction, but we don't have to because we know it's all 0. Now let's go to another. Let's say we are looking at this. This goes down, this goes left, found at a minimum distance of 2. We already have at 1, so why would we take another distance? So this would even travel further and that would not result into anything because that's a distance of 3 and we are already at a distance of 2. And like this, we would continue moving. When we are at this 0, we would move in the right direction at 1 and we would say, okay, I can assign it a distance of 1 and over here I have a distance of 2. So I found a better distance. So let's remove it and assign it 1. And this can go further from over here also. We can find a distance of 1 to this one. So in the end, we end up with this matrix, which is the correct result because now we have these ones at a minimum distance of 1 from a 0. So when we start from zeros, we can solve this problem better without having to solve the same problem again and again. This would be the basic algorithm. Let's take a look at the code implementation to understand it better. So I am here in the code editor. I have this function given update matrix. It receives a matrix. It's a list of list and we are supposed to return a list of list of m cross n. M would be the number of rows and n would be the number of columns. So to keep things handy, let's first take the values of m and n, and because we are going to use it very often, let's say length of matrix, this would be number of rows m, and n would be length of matrix 0. Next up, what we would basically do is, since we want to traverse from every 0, how about we store it? How about we store every 0 index in a queue? So let's create a queue. Let's assign it to tqueue. We have a queue over here in Python. Now, in the matrix, let's manipulate this matrix itself. Let's use this matrix itself as a distance matrix. So the first thing I would need is, let's iterate through this matrix. Every time I have a 0, let's put that index in the queue. Every time I have a non-zero, let's say that the distance at that position is assigned to infinity. It's something like this. So if I have 0 1 0 0 0 0 1 0 0, if I have something like this, let's say that the distance, this matrix, I'm using it as a distance matrix 2. So over here the distance from 0 to 0 is 0 0. This over here I'm going to say infinity, and it's a positive infinity. Over here I'm going to say positive infinity. I'm going to say 0 0 0 0 0. This is what we want to do, so that this becomes a matrix which stores the distances. Every time I want to update the distance at these indexes, when I find a better distance, a minimum distance. So let's iterate through the matrix. For I in range m, for j in range n, if the matrix at I and j, if this is equals to 0, add it in the queue. The distance is already 0, so I don't have to worry about that. Queue dot append, I am appending a tuple of ij. This is the index. If it is not 0, then it is 1, and I can say matrix of ij. The distance over here would be, let's say, float of infinity. This assigns the value to positive infinity. Next, since we have this queue filled up, let's iterate through this queue. So while queue, let's take out the first element. Let's call it x comma y equals to q dot pop left. We took out the first element. Now, since we have the first element, let's go in all 4 directions. So I would do it something like for I comma j in, I would get all the 4 directions, which would be -1, -1 and 0. I can say 0 and -1. I can have 1 and 0. I can have 0 and 1. These would be all 4 directions we want to go. So let's assign those directions. xd, this is like x dash. It would be equal to x plus I. Y dash, this is a new direction. This would be equal to y plus j. Okay, this will give us all the 4 directions, but we also need to verify those directions are valid because they might be out of bound. So let's validate those directions. So if 0 is less than equal to xt, is less than length of a matrix, which would be basically m. We already calculated that value. Very similarly, this y should be inside the range less than n. Now we want to update the matrix every time we find a better value. Like we saw in our example, something like I had something like 0 0 0 0 1 1 0 0 0. In my example, this 0 was assigning this 1 a better value. Earlier, it was a value of 2, and then this 0 made it 1. So let's put that in condition. And how do we do that? So let's say if the value at this particular location from 0, it would be the right location, which means xd combination of this. Okay, from starting from xy over here is 0 and xd is over here, this location. So we can say if the value over here is larger than what this can give. So the value over here would be matrix of xt and yd if this value is greater than the value of matrix at xy, which means this location, xy, not only greater, but greater than this plus 1, because there is this distance which would be added. So now once this condition is satisfied, I want to go further and update the value at this location, which means matrix xt yd equals to matrix x and y plus 1. This should be the next distance. So once I'm over here, I want to proceed further and keep updating the values after this. And for that, I can say that, okay, I can take this queue and append this new index xt and yd so that I can move forward in a breadth first approach. xt, yd over here, and this should be it. So now this would traverse through the entire array starting from every 0 and assign the minimum values to all the indexes. This once we are done, this queue would end and we can return the matrix. Let's try to run this code. So we have a typo over here. It's not map, it's a matrix. It's passing. Let's submit it. Okay, so we have a solution.